Okay, good morning, everybody, and welcome to the webinar, Introduction to the Michigan Stream Quantification Tool. This webinar today is brought to you by the Michigan Department of Environment, Great Lakes and Energy, as well as Ecosystem Planning and Restoration and Stream Mechanics. I'm going to go over just a few brief housekeeping things to start out. If you would like a certificate of completion for this webinar, you can email me at michigan@michigan.gov. There are supposed to be close to 150 people on this meeting today, so we're asking if everyone could please mute their microphones during the presentations, just to keep everything running on time and moving smoothly. If you have any questions during the presentation, please type those into the chat feature. Of the three of us, Will and Sarah and myself, whoever's not presenting will be moderating the chat feature, and will either answer the question in the chat or they may choose to interrupt the presenter to ask the question. And then after each presentation, we'll take a brief pause for any additional questions that people might want to ask. The webinar will be recorded and posted for future viewing. So I would give it a couple weeks, but I would check at michigan.gov/lakes and streams, and that's where the webinar should be posted. So today's agenda, we're going to start out with some introductions and an overview of the tool development, and myself and Alyssa Riley from EGLE are going to do that. And then Will Harmon is going to do an overview of the stream functions pyramid framework and an overview of key parameters and metrics. And that will take us up to approximately noon, where we'll take a lunch break for about an hour. And then when we come back, Sarah Donatich will do an introduction to the Michigan SQT and the debit tool, and then a tour of the Michigan SQT user manuals. And then finally, we'll wrap up with a tour of the Michigan SQT using a case study, and Will's going to walk us through that. And then finally, we'll have a little bit of time at the end. I'll talk about next steps, and we'll have additional questions and answers. So today's presenters, we have Will Harmon with us. He's the owner and principal fluvial geomorphologist at Stream Mechanics. He has 29 years of experience in fluvial geomorphology and stream restoration. He's worked in both the public and private sector, but most recently he's been both a practitioner and an educator, and has worked on stream assessment and restoration projects throughout the US. And he's the developer of the stream function pyramid framework and a co-developer of the SQT. We also have with us Sarah Donatich. She's an ecological engineer in training and an environmental scientist at Ecosystem Planning and Restoration. She's worked with other states to help develop their SQTs, and her graduate research work at North Carolina State University evaluated the first SQT developed for North Carolina. So we're going to do a little overview of the development of the Michigan SQT. The stream function pyramid framework was developed in 2012. Several of us from Michigan were fortunate enough to go to free training on this that was held by EPA in Chicago in 2012. So that was really our first introduction to this idea. The first SQT was completed for North Carolina in 2016, and several other states followed suit in short order, and regionalization for the SQT has happened in Tennessee, Wyoming, Colorado, and Minnesota. South Carolina and Georgia are in the process of their regionalization, as Michigan is. Michigan began to work with Stream Mechanics to regionalize this SQT in late 2017. And this came out of a desire by different agencies and programs within Michigan to be able to quantify improvements to stream functions from restoration projects. The funding for the development of this SQT came from EGLE through US EPA grants, and also from the Grand Traverse Band of Ottawa Chippewa Indians through a Bureau of Indian Affairs and Great Lakes Restoration Initiative grants. So I'm going to talk a little bit about how the regionalization process and how the tool was regionalized for Michigan. Other states followed similar processes, but the stream quantification tool is based on the stream function pyramid framework. Like I said, other states have developed the SQT, and it's regionalized uniquely and specifically for each of those states. So the first thing that we did was to form an advisory team and technical work groups. And you can see on the right the representation that was on the advisory team for the Michigan SQT. The team was chaired by EGLE, and it included agency representatives with expertise in stream hydrology, hydraulics, geomorphology, physicochemical, or biology functions. And that advisory team was divided into technical sub-teams. We had a sub-team that met and discussed hydrology, hydraulics, and geomorphology functional groups, and then a separate team that discussed physicochemical and biology functions. And there were some overlap between those teams. And we had a series of web meetings and email communications over about 8 months in 2018 to really regionalize this tool. So part of the regionalization process is to select the parameters and the measurement methods that would go into the Michigan SQT. So that was one of the tasks that the advisory team and technical work groups performed. And then upon selecting those different parameters and measurement methods that we thought would be most useful for Michigan, a next step was to collect data, both any data that already existed as well as some new data in order to inform the performance standards. Where there was limited data, we also based some of the performance standards on literature and also best professional judgment of the advisory team members and other state experts who were invited to participate. So once those metrics and measurement methods had been set up and performance curves created, then Will and Sarah and Sydney could set about creating the Michigan-specific SQT spreadsheet and user manuals. There's 2 user manuals, a data collection and analysis manual, and that includes a rapid assessment method, and then a spreadsheet user manual that really explains the tool itself and what values are to be entered and how to go about that. And then sort of the final step in the regionalization process is development of a debit determination process, or our debit tool, and that part of it is currently under development. So I'm going to talk just briefly about the uses of the Michigan stream quantification tool. Today's presentations will focus on the SQT and how it works. The SQT is really intended for use by anyone interested in quantifying functional changes from a project. So this is not just something that will be used by EGLE, by the state agencies, but other agencies and groups have also shown interest in using the SQT to look at improvements from restoration projects. Within EGLE, guidance for use of the SQT will be specific to each EGLE program. And while it's not the focus of today's webinar, I am going to talk briefly about how the EGLE Resources Permitting Program plans to use the SQT, and then Alyssa Riley is going to talk a little bit about its use in the non-point source program. But briefly, the Resources Permitting Program is planning to use the SQT to assess stream function at project sites, and then also use it to evaluate proposed mitigation. And the non-point source program would like to use the SQT to demonstrate success for their grant-funded projects. So the Resource Permitting Program like I said, the SQT is intended to be used to evaluate impacts to stream functions at a project site, and then to determine if lost functions are replaced at a mitigation site. Now, the use of this SQT is intended for stream projects that may have more significant impacts and could need mitigation. So some examples of that are longer enclosures, reaches of bank armoring, channelization, or relocations. And we suggest discussing SQT applicability with EGLE staff at the pre-application meeting. I do want to say that the SQT is not necessary for common projects that minimize impacts, for example, MPGPs. So we're not intending to use this on all of our projects. It's mostly for the projects that have larger impacts that could potentially need mitigation. And now I will turn it over to Alyssa Riley. Alyssa, if you're with us.
Yeah, thanks, Bethany. So the non-point source program is funded through Section 319 money. And as a condition of receiving that funding, we are required to report our success stories to EPA on an annual basis. And so we've been doing this for a number of years, and we address a variety of problems and try to use a variety of parameters to show success in. And so what we're really talking about here is BMP effectiveness monitoring. And so we need to get some monitoring before a BMP is installed, and then we get post monitoring to try to show that success. And so what we want to do with the Michigan SQT is demonstrate functional lift in a variety of parameters. Next slide. And so we have used the thought process of functional lift in past success stories. For example, a few years ago, we wrote a success story for a two-stage channel that was installed in Bradley Drain. And you could go to the next slide. And so, like I mentioned, we have used this thought process, but then what we really want to be able to do with the SQT is quantify that functional lift and expand the parameters that we can do. And this won't apply to all of our projects, nor will every parameter apply to all of our projects. But we'll be able to select the ones that we anticipate our projects would have an impact on. You could go to the next slide. And we are interested in trying to document success in not just our projects, but any project where we could potentially have a role in that monitoring. And we are interested in short-term success stories. Some restoration projects will have a more immediate impact on certain parameters that are lower in the pyramid levels. But then we're also interested in tracking long-term successes and trying to track that to be able to demonstrate that functional lift in the higher categories. And so if you ever have any idea of any project where you show success and maybe we could play a role, please contact me. So that's it.
Thanks, Alyssa. Okay, so that is our overview of the tool development, and I'm going to go ahead and let Will get started talking about the stream function pyramid framework.
All right, give me just a second to get everything organized over here. Okay, thanks, Bethany. All right, so we're going to do two things before lunch. We're going to first do a presentation on the stream functions pyramid and the stream functions pyramid framework, because that is the logic or the concept, the thought process behind the stream quantification tool. And as I do this, I'll be introducing different parameters and metrics. So the next presentation will give a little bit more information on that. And Bethany, if you will you mute? Because I'm getting a little bit of feedback. I don't know if that's because you're not muted. Okay, hopefully that's a little bit better. I think so. Thank you. And then so I'll spend some time on the parameters and metrics. That'll take us to lunch, and then after lunch, it'll really be all about the SQT itself. So this is a preamble to the SQT. And really want to start just very big picture, because we have all sorts of different folks on this webinar, people who work in stream restoration, stream mitigation, geomorphologist engineers. We have folks that work more on the permitting impact side, and maybe historically have done more wetland type of delineation and impact and restoration. So I just want to kind of try to speak to everyone and just start with a picture of a lot of different streams, and just kind of make the point that stream systems come in all different sizes and shapes and personalities. We have streams that are in low gradient valleys and have this meandering nature and personality. We have streams in steep gradient settings that are more of a step pool system. We have streams that are in humid environments and are perennial streams, or large and perennial. We have ephemeral streams that only carry water during precipitation events. We have single thread channels. We have multi-thread channels. So there's a lot of differences in the way streams function, but there are also commonalities between these systems. All of these streams are transporting water and transporting sediment and interacting with their boundary condition, just at different rates and in different ways. And so so that's part of the goal here, is to create or provide a model or concept or framework where we can think about the similarities and differences among these systems, and more importantly, think about it from the perspective of stream restoration. And so to make this even a little more challenging, we have the issue that each of us in this meeting are seeing these slides. We see streams. When we go out to that stream on any given day, we see that stream through the lens of our training and experience. We are each a product of our academic training and our practical experience. So if you ask an engineer what's a function of a stream, the first thing most engineers will say is to transport water. And that is a function of a stream, but it is not the only function of a stream. And then if you ask the geologist or geomorphologist what's the function of a stream, they'll talk about sediment transport, maybe large wood transport and storage. But we're typically interested in, why does this stream system look and behave the way it does given the landscape setting that it's in? And sediment and wood transport and storage are also functions of a stream, but again, not the only function. And then if you ask the ecologist what's a function of a stream, you're going to get a report on the life histories of aquatic organisms and their relationship to the habitats that they need to exist. They may talk about stream metabolism, nutrient cycling, and again, these life histories of organisms. And those are all functions of a stream as well. And so the challenge can be, how do we bring these groups of people together to work under that common goal of stream restoration? And it's made even a little bit more difficult with the whole idea or notion of restoration. This document from AGU is kind of I think captures really what I was just saying in picture form, which is stream restoration is a catch-all term. and it's used to describe a wide range of management actions and is such difficult to define. The definition of restoration can vary with the perspective or discipline of the practitioner, so that's what I was just showing, or with the temporal and spatial scale under consideration. And we've really seen this. I could spend the next 30 minutes talking about all the challenges that we have just nationally and programmatically with how one person or one group defines restoration versus another group. And so I want to narrow that for this discussion and our application. And we primarily focus on the federal mitigation rule definition of stream restoration, where restoration means the manipulation of the physical, chemical, or biological characteristics of a site with the goal of returning natural/historic functions to a former or degraded aquatic resource. And then they lump reestablishment and rehabilitation underneath the restoration goal. But to me, what's significant and what's important about this definition is that it includes the word manipulation. So it implies that we as practitioners will go out to a site and do something. There is some restoration activity, and the purpose of that activity is to return physical, chemical, or biological characteristics to a natural condition or a historic condition or function. And I will just kind of make one request as we're going forward. I do hear a little bit of background noise, so if you have not muted, if you will go ahead and do that. And Sarah, maybe if you can kind of look at people and see that they are not muted, I think you could mute them. So that would be great. Thanks. All right, so now we'll get into the stream functions pyramid. And as I mentioned, kind of coming into this, it is a concept. You know, this is a way of thinking about stream functions. It is not the only way to think about stream functions, but it is a way to think about stream functions that support each other to create a healthy stream corridor. And I say that because this is not about ecological services. This is not a diagram or framework that says, how do streams function to help human activity? That's an ecosystem service. This is what stream, how can we organize stream functions to acknowledge how they support each other in order to have a healthy, natural aquatic stream system. It's also for the restoration practitioner. This is not meant to be a framework that shows all of the interrelationships among functions. It is to think through stream restoration as a practice. So the primary thought process is this. If you want to achieve a certain level of restoration, know what supporting functions you need. And so now I'll kind of dive into the pyramid itself and we'll walk through that. So this is the stream functions pyramid. You'll notice at the bottom, we have geology and climate that's supporting and kind of driving all of the functions above. This is why streams in Michigan look different than streams in Arizona. You have different geology, different climate, different than even streams in North Carolina. Even though we have some similarities, we do have different geology, different climate. So there are 5 functional categories to this pyramid. So this phrase, functional category, try to put that to memory. There are 5. So at the base of this pyramid is hydrology. Then we have hydraulics. 3rd is geomorphology. 4th is physicochemical with a C, physicochemical. And then 5 is biology. With each functional category, there is a functional statement. And so the functional statement for hydrology is the transport of water from the watershed to the channel. And then once that water gets to the channel, we have the hydraulic functions. That is the transport of water in the channel, on the floodplain, and through sediments. And of course, hydrology and hydraulics are working together. We kind of acknowledge that with a dashed line between the categories, but generally we've got water coming from the watershed first. This is how we're thinking about it. And then water, once it gets to the channel, moving in the channel on the floodplain and through sediments. And then third, once that water is moving, it can do work. And that's the geomorphology category. It is the transport of wood and sediment to create diverse bed forms and dynamic equilibrium. And you could think of diverse bed forms as in-stream habitat, riffle pool sequence, for example. And you could think of dynamic equilibrium as a fancy way of just talking about channel stability. It just acknowledges that you can have a stable channel that doesn't necessarily stay at the same location on the landscape. And then once those processes are working, we can have the physicochemical processes, which is the temperature and oxygen regulation, the processing of organic matter and nutrients. And then finally on top is biology, which is the biodiversity and the life histories of aquatic and riparian life. Now, if I had to do this over again, I would add a word to this functional statement in biology, and that word would be animal. So it would read biodiversity and the life histories of aquatic and riparian animal life. That really is the thought process here. And again, I'm going to keep going through kind of the concept and the thought process, but keep that in mind or make yourself a note that really it's about aquatic animal life being the biology. All right, so I just want to show how the pyramid can overlay onto the Clean Water Act definition of function, which is the physical, chemical, and biological processes that occur in ecosystems. So from that stream perspective, these bottom three are more of our physical processes transitioning into the chemical and then into the biological. But this next slide to me is the primary benefit, I guess, of this thought process as it relates to stream restoration. And that is these lower level functions are more of your cause and your higher order functions are more of your effect. And here's what I mean. Let's think about a stream restoration project, and maybe our goal was to improve a certain fish species. That would be in biology. Our question then would be, what are the limiting factors, or what are the functions that we need in physicochemical, geomorphology, hydraulics, and hydrology to support that fish species? It recognizes that we're not going, if we have a degraded stream that's lacking a certain fish species, we can't just take buckets of that fish, dump it into the stream reach and say, you are restored, have a nice life. Because there are all these limiting factors that are preventing that fish from being there. And so that's what I mean by these levels, these lower levels being more of the cause and the upper levels being more of the effect. What do we need to have in place in order to meet those goals? Now, if we were in person and doing this, usually someone will raise their hand about now with a really sly look on their face, and they'll see this cause moving up to effect, and they'll say, what about beavers? Right? What about beavers? So where would beavers reside on this framework? They would be in biology. They are an animal life form that uses the in-stream and riparian habitat. And we know that beavers could be a cause that affect changes all the way down here into hydrology. And that's okay. It does not mean this thought process doesn't work. Remember, this thought process is not meant to be a framework that shows all of the interrelationships among functions. It is meant to be a thought process that says, if you want to restore something, what do you need to have below that in these other categories to achieve that goal? And with that thought process, the beaver example works, because we would say, if you want to have a healthy beaver population, what functions in physicochemical, geomorphology, hydraulics, and hydrology must be in place in order to support a healthy beaver community. All right, so the next sort of way of thinking about this framework is that first, the hydrology category as a restoration practitioner is typically an independent variable, meaning we're not going to change the hydrology of a watershed through our restoration activities. That is a general statement and not an always statement. If you're working in small headwater systems and you do have the ability to change the runoff relationship in that watershed through stormwater BMPs or massive watershed scale planting, then you could potentially change some of these hydrology variables. However, the hydraulic and geomorphology categories is really where the action is. That's where stream restoration practitioners spend the most time manipulating parameters and processes in these two categories to yield a result. And then the physicochemical and biology have a little bit more to do with site selection in terms of showing improvement than the reach scale improvements alone. So think about if you have a reach that's in really bad shape, but you have a really healthy watershed above it, that's what I mean by site selection. You fix the reach problems and you may see dramatically good improvements in physicochemical and biology as a result of your work. But if you have Detroit upstream of your project reach and you do a lot of work in the reach, you may not see any improvements in physicochemical or biology because the upstream watershed doesn't support that. Or maybe you see a little bit, but not very much. So that's what I mean by the site selection. And I'll get into a little bit more detail with that when I talk about restoration potential. All right, so why do we need this concept? From the restoration side, for those of you that are working as restoration practitioners or restoration mitigation side, it is so we can quantify functional lift. I think we will all agree that the picture in the lower right looks better than the picture in the left, but how much better? The framework helps to think through that, and the SQT quantifies that. And the mitigation rule sets up a framework for saying really that we should do that, where the number of credits should reflect the difference between pre and post compensatory mitigation project site conditions as determined by a functional or condition assessment or other suitable metric. So that's really what we're trying to do with the SQT, is to show that difference in what these baseline functions would be before restoration, what the functions are after restoration, and to calculate the delta or the difference. We will call this functional lift. And in a mitigation policy world, if we are going to do that on the restoration side or the credit side, and I do use the word credit kind of loosely in this presentation just to kind of mean the restoration side and the debit to mean the loss side, that's really, credits and debits are mostly used in third-party mitigation, so I'm taking a little bit of liberty with that, so please forgive me, but I just mean credits to be functional lift on the restoration side and debits to mean functional loss on the impact side. But if we are going to talk about a way to quantify functional lift, we must use the same method to talk about functional loss. So again, if we look at these pictures, hopefully we all agree that the picture on the right looks worse than the picture on the left. So if you took this stream and made it look like this, there is functional loss. And then the question is, how much loss is there? I tend to think of this programmatically as credits should follow debits. And what do I mean by that? Is that the credit method should follow the debit method to make sure that there is parity between the two. So we want a credit to offset a debit. And the only way that can happen is if we're doing the same things on both sides of the ledger. All right, so I think we do still have a microphone or two on, so just another reminder, if you are not muted, if you would mute, that would be awesome.
Well, can I do a hard mute? This is Sarah, just because I'm
Yes.
trying to monitor that, but that might be easier.
Muted.
I'll just
Unmuted. Muted.
Oop.
Unmuted.
Okay, you should be good.
All right, yep, I'm unmuted. Okay, thank you. All right, so that was the pyramid. So next we're going to dive down into the framework. So the framework is just adding more detail to the pyramid. So we just went over the pyramid. In the framework, that's sort of your broad level view. We talked about these functional categories and functional statements. And so now I'm going to talk about function-based parameters, measurement methods, which have now really been changed to metrics. So if you go and read the original Stream Functions Pyramid Framework document, it's a short read. It's like 340 pages or so. We use the term measurement method in that document, but most SQTs now use the word metrics. So I have tried to be consistent from here forward with just saying metrics. Metrics are tied to parameters. Parameters help us understand that functional statement, and metrics are quantifying the parameter. And then we have in the original document what we called performance standards. Now we're changing that to reference standards, and then we put these into buckets of functioning, functioning at risk, or not functioning. I will go over this in detail. I just wanted you to see kind of an overview, a diagram, if you will, of what this framework looks like. So within every functional category, there are function-based parameters. Tied to every parameter, there is at least one metric, and tied to the metrics are these reference standards. So it's important to visualize this, because not only is this the way the framework works, it is how the SQT is organized. All right, so I'm going to do this kind of quick. We're going to go back through the pyramid and just show you examples of the parameters that are in each category. I'm not going to define them at this point, but the parameters that are in black font are the parameters that were in the original pyramid document. The parameters that are in red were added as we developed SQTs across the country. And the one that's highlighted in yellow is a parameter that is in the Michigan SQT. And so you'll notice as we go through here, the Michigan SQT does not include all parameters that are in the framework. That is normal. There is no SQT that includes every parameter that is described in the framework. And that's the way it should be. The framework is bigger picture. And then from that framework, it's sort of a menu of options. You pick the parameters that are most appropriate for your tool. All right, so in hydraulics, you'll see there was one added flow alteration, and then the one that's included in the Michigan SQT is floodplain connectivity. I'll be defining these parameters in the next presentation. Geomorphology has the most parameters. You can see that riparian vegetation is in geomorphology, which is why I wish I had added the word animal to my biology functional statement. There is good reason for putting riparian vegetation in geomorphology. I'll get into that a little bit when I do the parameter presentation. And then physicochemical, you can see the list. Again, you could kind of look here and say, well, bacteria is really, a form of biology as well. But, you don't have restoration goals that say, I want to return the bacteria of this stream to natural levels. Bacteria is pretty much always a water quality based parameter. Usually with the SQT, it's related to the activity would be like cattle removal from a stream. And so because of its relationship to water quality, it's put in the physicochemical. This is kind of your water quality category. And then finally, for the biology, pretty much every SQT has macroinvertebrate communities and fish communities. The There is interest, Joe, in putting mussels in biology. Michigan has even taken some steps to kind of look at that, but we're not quite there yet. Other states have expressed interest in either mussels. Some of the states where they have large ephemeral systems are very interested in adding amphibians. I think all of those would be awesome. We currently do not have SQTs that have these other critters in them, but all of them do have macroinvertebrates and fish, which is the most common focus for a stream restoration project. All right, so those are function-based parameters. So now attached to those function-based parameters are measurement methods or metrics. All I want you to know at this point in the presentation is that every parameter must have at least one metric attached to it, and it can have more than one. So every parameter has one or more metrics that quantify the parameter. And then attached to each of those metrics are reference standards, and those reference standards are put into these categories of functioning, functioning at risk, or not functioning. So those reference standards are based on this definition. It is the subset of reference aquatic resources that are least disturbed and exhibit the highest level of functions. This condition is considered functioning for the metric being assessed and ranges from least disturbed to pristine condition. So you will see this definition again when Sarah does her presentation. And what we do with the SQT is we put a value to this range. So there is a range of values from least disturbed with the ultimate being pristine. What's important to know with this is that reference standard is not equal to a best achievable or best attainable. Yes, best attainable by definition is the best we can do as stream restoration practitioners. Most of the time in the SQT, we are not holding you to a reference standard. Some parameters, yes, many parameters, no, meaning you do not have to get that parameter into reference standard. We're going to focus on the lift or the delta. What was it when you started and what is it when you finished? Because of that, we have to use this definition. Every scale must be the same. All right, so almost done with this presentation. Just want to acknowledge that there are some differences between the framework and the SQT. What I have been sharing with you is the Stream Functions Pyramid framework. If you read the big document, you do read 300 and some pages, and at the end of it, we still have not told you, or we still have not given you an assessment method. We've given you a framework to develop your own assessment method. Now, the framework does give reference standards at the measurement method or metric level, but it requires the practitioner to use their best professional judgment to roll up scores to the parameter, the category, and the overall condition. So now you insert the SQT. The whole deal with the SQT is that it removes that judgment, professional judgment process from the framework. It is an assessment method in a sense, but more than anything, it is a quantification tool that takes all of these parameters and metrics, puts it on the same scale, and gives you a scoring method. All right, so the last little thing I want to mention in this intro is that out of the framework document, we do recommend some applications. And so we talk about how you could use the framework to develop assessments. And again, the stream quantification tool is an assessment method out of the framework. We also talk about how you can use this concept to think about debit and credit determination in a way that would create parity. And then my favorite, actually, the low-hanging fruit, is that it does give you a way to think about developing function-based goals and objectives, and restoration potential. Unfortunately, I'm not going to do much on the goals and objectives part today, but I do want to just mention the restoration potential to kind of end this presentation, because this is built into the SQT. As the SQT, even though it is a quantification tool, there is a component to it that addresses restoration potential, which is the highest level of restoration that can be achieved based on watershed conditions, results of the function-based assessment, and any project constraints that you'll have. And by highest level, I do mean highest level on the pyramid. Typically, it's either through geomorphology or through biology, depending on what your upstream watershed looks like. So you can kind of see that in these pictures. Do you have a really nice forest upstream of your project reach? If so, your restoration potential is likely through biology. Or are you like this picture where you have Charlotte upstream of your project reach, and you might be able to do some good things with stability and habitat. You might even see some improvement in physicochemical and biology, but this biology is never going to look like the biology of this stream. And so the restoration potential is lower. So in the SQT, we sort of capture that whole thought process by having people say or determine the restoration potential is full restoration. And I'll just go ahead and spoiler alert, like these projects are few and far between. To have full restoration potential means you are communicating that you believe you can take this stream back to reference condition for biology. It does happen, but it doesn't happen often. More common is the partial restoration, where you are returning the channel to a stable system, you're improving habitat, you might achieve functioning through geomorphology, and you might even have some lift or improvement in physicochemical and biology, which are levels 4 and 5, but you're probably not going to take it to a reference condition. All right, so that's it for the pyramid. Sarah, if there's anything I need to address while I'm switching presentation.
You're good. Yeah, you're good. Not too many questions.
Smart group. Well, either that or I'm really boring. Okay, so now we're gonna change gears, switch gears for just a little bit, and I do want to spend some time going into a little bit more detail with these key parameters and metrics. All right, so what I'm going to do with this presentation is I'm going to focus on the required parameters and metrics, meaning they are required for all restoration projects. There's a little bit of a caveat to this. That statement is true in general, but you'll notice as I go through here that there are some cases where I will say you do not need to measure this metric if this condition is being met. So keep that in mind. And if we have time at the end of this presentation, I'm going to show you a spreadsheet called the List of Metrics spreadsheet. And it provides, it's a pretty nice little one-stop shop for showing you all of the parameters, metrics, how they're stratified, and what their reference standards are. If I don't have time, just know that that spreadsheet exists. All right, so I think we may have had some folks join us or some folks came off mute. So just another reminder, if you are not on mute, if you could mute yourself, that'll just help. With so many people, it helps to have everybody on mute. All right, so I'm going to go through the categories. We're going to hit hydrology, hydraulics, geomorphology, and then I'm going to focus on these parameters: reach runoff, floodplain connectivity, lateral migration, riparian vegetation, bed form diversity, large woody debris, and then I'll touch on the metrics that are associated with these parameters. This presentation is a little more in the weeds than the first one, so this would probably be a good one just to know that this is recorded. So if you want to go back over the weekend. What could be more fun than to listen to descriptions of these parameters and metrics again? I also know, and this slide may be more of a reminder for me than you, because I have to be careful not to get too much into the weeds with this presentation. I'm pretty passionate about these parameters and metrics, so I could spend the rest of the day just on one. In fact, when we do this as a course, we spend 4.5 days on these parameters and metrics. So this is going to be just an overview, and I'm going to focus on the what and the why and not on the how. And so what I mean by that is we're going to talk about what are the parameters and metrics that are included in the SQT and why are they important. I'll also touch on reference standards, but I'm not going to do that in detail.
Muted. Unmuted.
All right, so the first parameter is reach runoff. This is part of the hydrology category. And just remember, I'm not going to always be, putting the functional statement kind of back into view. But remember, these parameters their purpose in life is to help us understand that functional statement. So we're going to start in hydrology. The parameter is reach runoff, and that parameter is helping us understand how water moves from the watershed to the channel. And we're going to do that by assessing the runoff potential from land uses that are adjacent to the project reach. This is why we call it reach runoff and not watershed runoff or catchment runoff. And we're going to quantify it two ways. We're going to use two metrics called land use coefficient and concentrated flow points. So we'll do the land use coefficient first. And so the first thing we would do, or the first thing to note, is this blue line is our project stream reach. And so at the downstream end of that reach, we would delineate the watershed boundary, the entire watershed. So in this example, it's a small 168 acre watershed. That's step one. Step two is we would come to the upstream end and delineate the watershed that comes to the beginning of the reach. That's 112 acres. So we are left with 56 acres of lateral drainage area. This is the drainage area that's draining water from the watershed to the channel, but only between the upstream and downstream limits. So for the land use coefficient, what we will be doing, from a restoration side, actually from either side, is looking at lift and loss by land use change. So think about that. Reach runoff, the activity associated with the land use coefficient is changing the land use. The way we will capture that change is with what we call either a weighted curve number or a weighted land use coefficient. And so this calculation is the product of runoff potential, and that's a coefficient. It's a number. As that number increases, your runoff potential increases. And we're going to multiply that coefficient times the land use acreage. And don't worry about the coefficients. Those coefficients are provided in the user manual. So as someone who's working with this, again, it's mostly a desktop activity, and you're going to be delineating land uses. It's kind of a GIS drill. The reference standards for this come from a manual, NRCS manual for TR55 values. So they are literature provided, or provided by the literature. So here's a picture example of what I'm talking about. So here's our stream. This would be like part of the project reach. And as we look adjacent, we can see the watershed divide is up here along this ridge, along the woodland. And you can kind of see a swale here. So overland flow or reach runoff could kind of concentrate in this swale and move down the hill slope into the valley bottom and then into the stream. And as it does that, it's moving across different land uses. We have cropland here. And so you would delineate this area and then look in the manual, and there's a coefficient assigned to this cropland. And then you would have grassland here, or grasses. You would delineate that acreage, and there would be a coefficient to assign to this grass. And so as if this was a restoration site, especially up here on the hill slope, you have the opportunity to convert this from cropland back to forest, which is a better coefficient, and show your lift. And then likewise on the loss side, if this was all forest and you cleared all the forest, especially on the hill slopes, that would be the loss. So that's land use coefficient. The second metric for reach runoff is concentrated flow points, and that counts the number of concentrated flow points, which are ephemeral channels caused by human impacts. So that's important to remember. It is, if you have a natural ephemeral channel, that's not a concentrated flow point. But if we humans created a ditch, then that's a concentrated flow point. So it's anthropogenically created concentrated flow points. We just simply, for now, count them along the project reach and report it as a number per 1,000 feet. And so things that would count as concentrated flow point are farm ditches, parking lot ditches, and road ditches. Here is a classic urban example of a concentrated flow point. So we have a parking lot here, parkland, and a concrete swale that's bringing water right from the parking lot to the channel. And so the reason that we have concentrated flow points along with land use coefficient is because the land use coefficient could capture the change in land use for this park. So let's just say we convince the park to move this playground up onto a terrace and now allow us to plant this in trees. That change would show up as the land use coefficient change. But if you just left this concentrated flow point, you're short-circuiting the buffer, because all the water from the parking lot can come right through the buffer and into the channel. And so we wanted to create a way to incentivize the removal of these concentrated flow points while acknowledging that it's related to stream function as well. It is moving water from this watershed directly to the channel in an unnatural way. So that was an urban example. Here's an agricultural example from Michigan. So you can see our stream. This is during a storm event. So here's the stream, here's the cornfield, and here's the ditch, bringing all of this water right to the channel in quick fashion. And so while that's maybe good, perspective is everything here. Maybe as a farmer, you're glad about that because it's draining the field quickly, keeping your corn high and dry. From a stream and floodplain function perspective, it's a bad thing. And from a hydrology perspective, it's a bad thing because it is bringing all of this water from the watershed directly to the channel through a concentrated flow point. So we would want to remove that if we could as part of the restoration practice. And so here are some examples just to kind of give a little bit better picture. This is a pretty big river. This is in Wyoming. And you can see in this example, they cut these pipes, made a little forebay, and then they're spreading that water out on a level spreader. So that would be a restoration activity to get rid of a concentrated flow point. Here's another example where they cut the pipes and just made these sort of infiltration basins, like an oxbow pond, before getting to the channel. All right, so that is the only parameter that we have in hydrology for the Michigan SQT. We also have one parameter in hydraulics. That parameter is called floodplain connectivity. I would argue that it's potentially the most important parameter from a stream restoration perspective. It is part of the hydraulics functional category. And here's our functional statement again. The functional statement for hydraulics is the movement of water in the channel, on the floodplain, and through sediments. So floodplain connectivity is helping us understand how water moves in the channel and on the floodplain. It really is not capturing the through sediments, and most SQTs do not do this part. You would need some way to sort of measure surface subsurface interaction, and usually that would be a little bit more of an academic activity than a stream restoration activity. But we are capturing the water movement in the channel and on the floodplain. And so these pictures just kind of introduce that idea. Picture on the left here is this is a restoration project on a farm, and you can see water is right at the top of bank here. We would call this a bank full discharge. And then as soon as water gets above this, as soon as you have a little bit more discharge, then it can spread out onto a floodplain. And that's what you see here. This is downstream of this, and water is spreading out onto that floodplain. Now you can notice on this side, we don't have great riparian vegetation, but that's another parameter. All we're looking at here is the stream connected to the floodplain or not? So floodplain connectivity evaluates how connected the stream is to the adjacent floodplain or bankful bench. And I put this "or" here because we do have to acknowledge that floodplain connectivity varies by stream type. And I'll show you some examples in just a minute. You can't just use one set of reference curves for floodplain connectivity for all streams, because remember that first picture, streams come in all different shapes, sizes, and personalities. So we have to fit that parameter to those differences. So we use two metrics to quantify floodplain connectivity. One is the bank height ratio. It's not stratified, although it is regionalized. And then the entrenchment ratio, which is stratified by the Roskin stream type for its reference condition. Now, this particular parameter is regionalized by bankful width and depth, which is pretty nice. What that means is that our reference standards do not really vary across the country. If they vary just from improvements in the way that we've been thinking through reference standards, but they're not varying from the perspective of Michigan is different than North Carolina. Although you are different. A bankful discharge for a given drainage area is very different in Michigan than it is in North Carolina, but we are normalizing these values by that bankful dimension so the ratios are the same. Hopefully that makes sense. That's a little bit into the weeds, but just, from today's perspective, just recognize that we are regionalizing the value by having good bankful regional curves, for example. And you'll see that discussed in the user manual. All right, so back to this picture. Even though we don't have awesome riparian vegetation, we do have awesome floodplain connectivity. All flows greater than bankful are spreading onto this floodplain. This is a stream that is in an unconfined alluvial valley, meaning you would naturally have meandering processes. You have a wide floodplain, pretty low gradient floodplain. If you're into Roskin's classification, this would support a Roskin C or E stream type. So functioning floodplain connectivity. But this is also functioning floodplain connectivity, even though it's a very different system. This is a colluvial valley, this meaning the material in the bottom of this valley originated from the hill slopes. That's the definition of colluvium. And the stream is sort of working its way through those sediments. And so the white line is delineating the boundary of our floodplain. And you can see it's very small. It's really just a bankful bench on this side and a little bit of a bankful bench on that side. But that is what is natural for this system. So this is also functioning floodplain connectivity, even though it looks very different. This is the whole purpose behind what we call stratification of the reference curves for a given metric. All right, so again, I got to be careful here not to go into the weeds too much, but the two metrics, just to kind of show you the math, the bank height ratio is the first metric. It is just the depth of the channel on the lower of the two sides, so the top of low bank depth divided by your bank full depth. The thing to remember is that you want the answer here to be 1. A 1.0 bank height ratio is pristine. That means that bank full equals the top of the bank regardless of the landscape setting that you are in. And as that bank height ratio gets higher, it means your stream is becoming more incised. It's deeper than it should be. And so we have reference curves to reflect that. The entrenchment ratio is different. The entrenchment ratio is the flood-prone width divided by the bank full width. So that seems pretty easy. You could kind of think of it as valley width divided by bank full width. But there is a catch. That flood-prone width is measured at an elevation that's 2 times the bank full max depth. So it's not the valley width regardless of channel depth. You got to consider the channel depth with it. The reason this is important that goes with the bank height ratio is this says it says if water can hit the flat surface, the bench or the floodplain or former floodplain, how far can it spread? And so the two go pretty nicely together. You can kind of see that in this picture. This elevation is your low bank and bank full, so it has a low bank height ratio. Water is just above bank full discharge and is now spreading onto this bench, and then we would measure the width as the flood-prone width. So they go together. And I'll kind of show you some examples, some picture examples. So here's a restoration project back to an unconfined alluvial valley. You see the bank height ratio is 1, that's pristine, and the entrenchment ratio is greater than 10. That is also pristine. So it means that water can spread out over this unconfined alluvial valley. Back to our colluvial valley example. Again, the bank height ratio is 1. That's good. The entrenchment ratio is much less. It's only 1.8, but that is functioning for this valley and stream type. So the picture I just showed was an E stream type. Greater than 10 was pristine for that. This is a B stream type. The appropriate entrenchment ratio here is 1.8. That would be a pristine entrenchment ratio value here. Now this one's not. So now we're into an urban stream. This would be an F stream type. Bank full's down here. When we multiply that bank full depth times 2, it does not come out of the channel. And so your bank height ratio now is high, greater than 2, and your entrenchment ratio is low at 1.1. This would be not functioning for floodplain connectivity. And the reason is that this was an unconfined alluvial valley. And so the reference stream type here would be a C. So you're not comparing floodplain connectivity to an F, which is what it is. You're comparing it to what it should be, which is a C. And that's why it would be not functioning. All right, so that's floodplain connectivity. So we've done reach runoff, we've done floodplain connectivity. The rest of this presentation will spend time in geomorphology. So just as a reminder, these are parameters and their metrics that help us understand the transport of wood and sediment to create diverse bed forms and support dynamic equilibrium. There are 4 parameters that we're going to go over: large woody debris, bed form diversity, lateral migration, and riparian vegetation. So we'll start with large woody debris first. So that's our parameter. Large woody debris is the function-based parameter, and the metric is the large woody debris index. So this is an existing assessment method. We did not create the large woody debris index. We adopted it from the U.S. Forest Service. It is a method that focuses on large wood within the channel. So this particular assessment method is not assessing large wood on the floodplain. And with this assessment method, you're going to look at a variety of things. You look at individual pieces of wood, you look at jams, and you kind of answer or measure different aspects of the wood. But in general, you're going to get higher scores, higher large woody debris index scores for larger pieces of wood that are closer to the stream bed and immobile. And the reason for that is that those factors are what drive more functional response than if you had a small piece of wood up near the top of the stream bank and it was easily transported by the river. Now, while this is a Forest Service method, we found that there was not a lot of guidance for answering some of the questions. So we have tried to kind of help answer questions and scenarios that you might see in the field. So there is a field manual for this on the Stream Mechanics webpage under the Resources tab. And we're actually working on an update right now, so you can get the current manual here. And I don't know, at some point in the future, I would like to say it'll be soon, but I don't know. At some point in the future, we'll have an updated manual. All right, so what is large woody debris? For it to be counted as large wood, it has to have a diameter of greater than 10 centimeters at the larger of the two ends, and it must be greater than 1 meter long. That's from the Forest Service manual. It needs to be dead and fallen. So if you had a dead tree standing on, kind of part ways up your bank, that's a snag. That is not large wood per this method. And as I mentioned, it does include jams and pieces. So in the foreground of this picture, this is a Michigan stream. You can see there's a piece of large wood here, 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 and here. So this would be assessed as a jam. It takes 3 or more pieces of large wood to equal a jam. And then downstream, here's another piece of large wood. That would be a single piece. So we both would be captured in this assessment method. So why do we include large woody debris in the SQT? Because it does create habitat and channel complexity. Large woody debris is a driver of many hydraulic and geomorphology functions. You can see a few listed here. Creates flow resistance for hydraulics. It can expose gravels on the downstream side of the wood, accumulate some sediment on the upstream side, trap organic matter. It is a good way to create channel complexity. You can kind of see that in this picture. Here's a piece of large wood in a very sand-dominated stream, but it's exposing some gravels here, creating deeper water, some refuge for fish, good fish habitat there. So I have enjoyed collecting, sort of enjoyed collecting large woody debris data in Michigan. You guys rock when it comes to large woody debris. You've got some of the highest scores that we've seen in doing this assessment method across the country. And so I'm going to take a little bit of a detour for just a minute with this particular parameter and show you how we develop the reference curves when we have local data. And so these are actually pictures from 2 of our reference sites. So we identified some sites in Michigan that had old forests. So we really kind of the way we are defining a potential reference reach for wood is that it's an 80-year-old forest or older, and there hasn't been wood management, meaning people aren't going into the stream and yanking out the wood. And so when we have that, then we go do this large woody debris index. We then take that data and create a box plot for it. So here's the box plot for large woody debris index for reference sites in Michigan. And you can see that the range is from a large woody debris index score of 1,000 up to about 3,300. That's the full range. we typically don't use the full range to set our reference standards, but rather we use the 25 and 75th percentile. And we sort of set the 25th percentile as that least disturbed and the 75th percentile as the pristine value. We do have some data from Michigan streams that are functioning at risk, meaning they have pretty good forest, but they're kind of teenage forests, like they might be a few decades old. There's some wood in the channel. Maybe they're doing some management to that wood. And so it's not meeting our definition of reference standard. So for large woody debris index, we took that 25th percentile value, which was about 1350 or so, and we made it the 0.7, which is the minimum value for reference standard. And then we took the 75th percentile, which is about 27 something, and we made it the 1.0. And so Sarah's going to get into more detail with kind of how this works, but basically the field value, the large woody debris index value is on the x-axis, and the SQT index value is, did I say that right? Field value, so the LWDI measured value on the x-axis, SQT index score on the y-axis. This point sets the beginning of reference. This point sets the pristine value. So as a restoration practitioner, you could put more wood in the channel, but once you get above 2700, it's just going to continue to return a 1.0. We did not use data to set the low end of functioning at risk, which would be right here at 0.3, but we did set the 0 value. So basically we said if you have 0 wood, you have 0 function. And then we just connected those dots to create this model. So that, and again, you're going to see that in more detail with Sarah, and then we'll see these reference curves at work when we play with one of the case studies. All right, so the next parameter is bed form diversity. For those of you that do not have a geomorphology background, you can think of bed form diversity like habitat. Basically, the bed form diversity parameter is a way to assess the riffle pool sequence in streams. And again, as you can see from this picture, we are acknowledging, or we are going to acknowledge, that bed form is very different in meandering streams and unconfined alluvial valleys with gravel bed material versus meandering streams maybe in sand bed systems or step pool systems, so gravel cobble bed systems, but in steeper environments. So there will be stratification that happens with bed form diversity as well. All right, so again, bed form diversity is assessing the condition of in-stream habitat, so think riffles and pools. It is a surrogate for assessing sediment transport processes, especially aggradation. So this is a criticism that sometimes I get with the SQT, especially from like hardcore modelers, engineers, modelers. They're like, hey, why don't you have sediment transport in the SQT? Sediment transport's one of the most important things to look at from a stream restoration perspective. And the reason for that is that the SQT, even the framework, is not a design tool. This is not where you're doing your design calculations. It's where you're testing your design calculations as they relate to reference condition. And so you would do your sediment transport calculations as part of the design process, and then we're going to use bed form diversity measurements to say, did you get those calculations right or wrong? Because if you got them wrong, it'll show up in the form of aggradation, which the bed form diversity will pick up. Your pools might fill up with sediment, or worse than that, your riffles might fill up with sediment. And then we capture degradation with the floodplain connectivity parameter that we just went over, bank height ratio in particular. So I would argue that sediment transport effects are in the SQT. We just do it through surrogates primarily through bed form diversity and floodplain connectivity. We're going to include 4 metrics with bed form diversity. I'll go over those in just a second. And then the reference standards for those metrics are from literature values. We are starting to develop a data set for Michigan, but we used a bigger, kind of not necessarily national, but a larger regional data set to help do these reference curves. And they are generally related or stratified to the Roskin stream type. All right, so here are our metrics. So we're going to always measure a pool spacing ratio, a pool depth ratio, and a percent riffle. And then if we have signs of aggradation, we will measure an aggradation ratio. So just to kind of show you some examples of that. So here's, this is a plan view of pool spacing and percent riffle. I'll show you how we would actually measure it, but just to conceptually understand the metric, this is a Roskin, it's actually a Roskin E stream, but this would apply to Roskin C and E stream types. And in this valley, which is an unconfined alluvial valley, pool spacing would be from the outside of one meander bend to the outside of the next meander bend. So at this point, think of that as your pool spacing. It's how far is it along the stream from this meander bend to this meander bend. But there is a little bit of a twist. You don't get to pick just anywhere in the meander bend. You're going to pick the deepest part of that bend. And so that does require going to the field and finding that location. And so in this environment, in this unconfined alluvial valley, meandering stream, that is your pool spacing. And you will measure it between every meander bend. In this environment, if there is a pool in the riffle, which would be right here, you would not measure that for pool spacing, but you would measure it for percent riffle. And so the riffle is essentially the crossovers between these bends, and you're going to measure those links. And from those links, you'll determine the overall percent riffle. So as I mentioned, I was sort of showing you that in a plan view to kind of help picture it. But in reality, you're going to go to the field and you're going to measure those values in the field. We in today are not going to get into you remember I said we're not going to focus on the how. And part of that how in the user manual will include a description of how you can do detailed assessments and rapid assessments. And there are different scenarios under which you would do rapid assessments versus detailed assessments. These are pictures of a detailed assessment where you're bringing surveying equipment out and you are surveying a longitudinal profile that you can use to make these calculations. And in the rapid method, you would just bring survey rods, tapes, hand levels, line levels, and you would more rapidly make these measurements. So here's an example of a profile. So if you did a detailed survey, then you would create a profile that looks something like this, where the brown line is the thaw-wag or center line station and elevation, and then you have a bankful line that goes through that, and even a top of bank line. And so the pool spacing is you're finding the deepest part of those pools, you're measuring that distance for each one, and we divide that by the bankful width so that we can normalize the data. This is a form of regionalization, or really normalization, but it's one way that we can use ratios from different states because we're normalizing or regionalizing that data to the bankful conditions that are appropriate for a specific region in a specific state. All right, so things are a little bit different if we have a steep gradient system. So this would be pool spacing and percent riffle in a Roskin B stream type. So here's a cascade into a pool, a step into another pool, and we would be measuring this spacing. So it's a very different process than the meandering process. Here's another example, long cascade. There's a step on the downstream end of that cascade with a monster pool. If we had more time, I would show you a GoPro video underwater of this pool. It is full of Arctic grayling. This is a shot from Alaska. It's awesome, but we don't have time. All right, so a few kind of things to think about when you're doing pool-to-pool spacing. One is the question about channelized streams. So what if we took a meandering stream and we straightened it? If we do that, then in the SQT, we would automatically equal a 0. So pool spacing ratio and channelized streams automatically equal 0. All right, so we're doing bed form diversity. The first metric was pool spacing ratio. The second metric is pool depth ratio. And so in the rapid method, you're pulling a tape, you've got your survey rod, and you're on the hunt for that deepest part of the pool. And then once you get there, you're going to measure the bankful pool depth. If you're surveying, same process, you're looking for the deepest part of the pool, but you're using survey instruments to measure that deepest part. And then the value here is the bankful pool depth divided by the riffle mean depth. Oh, let me just go back. So in this picture, these are base flow conditions. And so I kind of want to emphasize the bankful part of that. So if we were out here with the rapid method, the deepest part of that pool is about here. So we would measure from the bottom of the pool to water surface, and then from water surface up to bankful, which is the top of bank in this particular stream, and add those two together. So it is a bankful depth that we want and not a base flow depth. And then that gets divided by a riffle mean bankful depth. So we should really add the word bankful here. All right, the last metric is the aggradation ratio, and we would only use this ratio if there are signs of aggradation within the reach. So this kind of example is really a pretty nice watershed. It's a gravel bed stream, but there's been logging upstream in the past, and it released a lot of sand. And so these riffles are filling up with sand on top of the gravel and forming mid-channel bars. So if you have a gravel bed stream that has sand mid-channel bars in the riffle, that's where you would use the aggradation ratio. And the aggradation ratio is the width to depth ratio at that riffle, measured width to depth ratio, divided by the reference width to depth ratio. So as that number, the results of that equation gets higher, then your aggradation problem is getting worse. All right, a few more rules of thumb for bed form. So, I mentioned that bed form diversity is a required parameter, but there's some caveats. So if you are working in a multi-thread channel, and it needs to be a natural multi-thread channel, so a D or a DA, you would not measure bed form diversity. If you are working, and that would be kind of, here's a multi-thread channel from Alaska. Here's a bedrock channel. So if you truly had a channel that was on bedrock, then you would not do bed form diversity. If you had an ephemeral channel, you would not do bed form diversity. These are all pictures of places that are far from Michigan. And so I wanted to add this fourth one. This one is Michigan specific, because you do have this. If you have a naturally straight sand bed channel that looks like this, and this is loaded with wood, nice riparian vegetation, but it's just a straight section of a sand bed stream, the bed form diversity is not going to apply. Your large woody debris is what's driving the bed form complexity here, and we are exploring some ways to add a new metric for bed form diversity in these systems, but that's going to take a while. All right, the other question I often get with bed form diversity, I've been talking about riffles, and so the geomorphologists always like to call me out on this one because if you want to be the hardcore academic geomorphologist, riffles only exist in gravel bed streams. If you have sand bed streams, the bed forms are identified by dunes, anti-dunes, ripples with a P, dunes, and anti-dunes. We are being more general. So we do apply the term riffle to sand bed streams just for ease of use. And what we mean is the crossover. So if you have a sand bed stream in Michigan that is meandering, which you do, that crossover between one outside bend to the next outside bend, that crossover we are equating to the riffle. So it will apply. All right, so 2 more parameters before we're done. The next is lateral migration, and then we'll end with riparian vegetation. How do you like that for a cut bank? That's pretty big cut bank there. And just want to acknowledge sort of the processes for lateral migration. You know, if we were all together in a classroom, I would say, okay, who thinks stream bank erosion is bad? And I would make you raise your hand. And then I'd say, who thinks bank erosion is good? And I'd make you raise your hand. And then the right answer would be, it depends, which is usually the answer. And so the key to a meaningful life is to know what it depends on. And for lateral migration, it really depends on the rate of erosion and how that relates to reference condition. And so lateral migration is a natural process, and there are good things that come from it. A source of sediment. You know, we talk about sediment transport as being supply and transport. So you need a source. So bank erosion that supplies sediment can be a good thing. That can lead to increases in sinuosity, which can lead to increases in large woody debris. It can encourage new vegetation on new surfaces. So like as a meander bend slowly moves down valley and it exposes a new point bar, that new point bar grows with herbaceous vegetation and different species of vegetation than what you might have on the floodplain. And just overall, it increases floodplain complexity. So that's good, that's natural, that's reference condition. The con is simply too much of a good thing. You have sedimentation, and that too much erosion, too much sediment supply can lead to aggradation, which is the filling of the channel bed, the smothering of aquatic habitats, and then pollutants can be attached to that sediment. So things like phosphorus can be attached to it and other things. And then, of course, there's just the loss of property. So if we're working with farmers or homeowners or transportation departments, as that erosion begins to take out infrastructure or property, then the concern goes up. So the lateral migration parameter, we're going to assess the potential for stream banks to laterally erode beyond what would be considered natural. And we're going to include semi-quantitative, kind of geotechnical looks at the bank, as well as a hydraulic assessment of the bank. We've also added armoring. And so the first 2 metrics, this first part kind of looks at what if our bank erosion is too much, and then armoring is looking at it to say, do we have anthropogenic methods that are preventing meandering processes? And that would lead to a negative score as well. All right, so the metrics are a dominant B-high near bank stress. This is a Roskin method. It's an existing assessment method that we've just stuck into the SQT. It is one that takes some training and some practice to do. The bank erosion hazard index, or B-high component of that, is more of the geotechnical look at the bank. So we're going to measure bank height, measure bank angle, measure root depth if visible, estimate root density, estimate surface protection, and take a look at the bank materials. And based on all of that, we would get an answer that could range from very low to extreme. And then for near bank stress, that's more of the hydraulic look. So it says if water is hitting the bank, then there's more likelihood of erosion than if water is just sort of flowing parallel to the bank. And there's like 7 different ways that near bank stress can be assessed. The next metric, so that's one metric. Dominant B-high near bank stress is one metric. The second metric is percent stream bank erosion. So that is where you have erosion as identified from the dominant B-high near bank stress. How much do you have? What's the overall percent of your reach that is eroding? And then stream bank armoring is also as a percent. So what percent of your study reach is armored? So again, for a presentation like today, I'm not going to get into the weeds of showing, how we measure B-high or near bank stress, but I will sort of show you some, what it can look like when you do an assessment. So that big bank that I showed you to start with would have a B-high near bank stress rating of extreme, very high. So the B-high component is extreme because there's really nothing good about this bank. The bank height is huge. The bank angle is high. There's no surface protection. There's no root depth, no root density. Like it's kind of the only thing that can make it worse is if it was all sand. And so it's a very, very high eroding bank. It's on the outside of a meander bend that's quite tight. So it's also a very high near bank stress. So on the other end of the spectrum, this would be a functioning outside bend. And your B-high near bank stress here is low B-high with high near bank stress. So from a functional lift perspective, if you could go from this to this, the tool would capture that lift. Or if you went from this to this, the tool would capture that loss. And you might look at these pictures and go, well, that's unrealistic. You wouldn't have these banks in the same system. Well, not only are they in the same system, they are next to each other. This is the right bank of this stream, and then just past this picture is a riffle that crosses over to the left, and this is the next bank to the left. So this is hitting a floodplain, and this is hitting a terrace that's being a hayfield. So you could pretty easily do a restoration activity to go from this to this and capture that lift. So here's the armoring. Armoring is just any hard technique that prevents lateral migration. So things like riprap, gabions, concrete, etc. All right, so the last parameter that we'll go over before lunch is riparian vegetation. It is also one of, it's a required parameter that we're always going to assess. There are many sort of stream function or ecological benefits to having riparian vegetation or riparian buffer. So things like providing shade, things like providing organic matter via leaves and needles into the stream, dissipating energy and capturing sediment, on the floodplain. So having good floodplain vegetation slows down the floodwaters, encourages water and sediment storage. The presence of that vegetation then supports our nutrient uptake. It stabilizes our stream banks and provides that landscape connectivity or a corridor for organisms to move upstream and downstream. The metrics that are in the Michigan SQT are riparian width, average DBH, which is the diameter at breast height, tree density, native shrub/saplings, and native herbaceous cover. So this one you would only do if you were in a herbaceous reference vegetation community. So your riparian vegetation parameter is stratified in the Michigan SQT by that reference vegetation community. Is it a forested system? Naturally. Is it a scrub-shrub system? Naturally. Or is it naturally herbaceous system? So I'll just, again, to not get into the weeds with how to do all these measurements, I'll just sort of show you how it comes together from a practice perspective, back to this sort of great picture from an agricultural area. There's really no There's no buffer. I mean, this is a not functioning riparian corridor. We have a little bit of vegetation here, then mostly just cropland. So this would score very low in the SQT. This would be more of the reference condition look. Both of these are Michigan streams. And then the reference standards for this came from Michigan literature, kind of the lessons learned from the wetland mitigations, the wetland mitigation side and other forestry, BMP, and just forestry studies. And then our team coming together and using best professional judgment to form those curves. So I do just want to kind of end with a couple of thoughts that, sometimes it's not intuitive to people with this. A couple of things to say here. First, for those of you that are stream restoration practitioners on this call, especially if you work in other states that don't use an SQT, you will have to rewire your brain a little bit. Like, other than a few parameters, it's not about making you get to reference condition. There's not a requirement in the Michigan SQT that says your forest has to look like the picture on the right. It's about lift. Now, if you could do this, if you could go from a cornfield to a 100-year-old forest, which is what this is, that would be huge functional lift. But to do that and capture it in the SQT, you would literally have to measure it for 100 years. So you are proposing what you think that the value will be at the end of your monitoring phase, not at the end of the natural evolution of that vegetation. And so while this is awesome, you are not going to show it. You could not show an index value that goes from 0 to 1 with riparian vegetation unless you wanted to commit to monitoring for 100 years. And that's not bad. Don't let that freak you out, because you could do this to go from this site to something that looks like this, which is good. This would be kind of upper end of functioning at risk, and you would be going from 0 to something like a 0.6. That's a lot of lift. And Sarah is going to harp on this point a little bit more when we get into the SQT to help you guys really understand the difference between lift and quality. They do go together, but don't get hung up on the quality component. Focus on the lift component. But also, sort of a message to the restoration practitioners on the call, do not think you can put a 1.0 for all of your proposed condition scores. There are some that you can. Floodplain connectivity, you can hit pristine for floodplain connectivity. Riparian vegetation, the only way you could hit pristine for riparian vegetation is if you were already working in a forest that looked like this. And then if that's the case, yeah, you'd have this great pristine value, but you'd have no lift. And so it's about the lift. And then just to kind of end on a loss note, if you did convert a forest that was an old forest to parkland, then that would be we would capture that as functional loss. Okay, so that is it. So Sarah or Bethany, any questions I need to address or anything you two want to add?
Will, there was one question regarding reference data collected for Beehi near bank stress in Michigan, and I'm not sure.
So there is
about that.
I almost misspoke. I get my states mixed up sometimes. I was going to say there is data for Beehi near bank stress. I don't know. I don't think that's true, Bethany, but correct me if I'm wrong. But
no, I don't think so.
So we really don't need to regionalize Beehi near bank stress. We basically regionalize it by those categories. So we say, these Beehi near bank stress categories are in the functioning range. These are functioning at risk, and these are not functioning. And for the most part, that is that is used uniformly from state to state, because it is a bank specific assessment. It's taking into account, for example, what the bank material is, what the vegetation is. I will say where that can get a little bit tricky is working in some states like Colorado, where you have desert environments and you kind of naturally have some systems that are laterally unstable. And so the decision then is, well, there may be some behind near bank stress scores that would be higher naturally in those settings than here. But for Michigan, that's not the case. Your rates of lateral migration are naturally quite low.
Well, that was it for questions in the chat so far.
All right, I'm gonna show you this spreadsheet real quick then, since we have a minute. And again, I am not going to go into detail here. I just want to make you aware that once we make the SQT and the documents available, this is a document that you'll have. And so it's just a spreadsheet that lists the functional categories, the parameters, the metrics, and the units that the metrics are measured in. And then you have two columns that give you some information on reference standard stratification. So for example, we just talked about riparian veg. You can see that it is stratified by reference vegetation community, and then it is stratified by forest, shrub, or herbaceous. And then if we scroll over, then you can see how we went about creating those reference curves. So these are the not functioning range 0 to 0.29, functioning at risk 0.3 to 0.69, functioning 0.7 to 1, and then where you see values, that's where we put the values in order to create the model. So Sarah will show you some of those results, or sort of how that works with the SQT after lunch, and then I'll show you where all these curves live within the SQT after that. All right, if there are, yep.
Well, we had another question about, is there a measure of native versus non-native plant species in the buffer, especially when considering both can benefit a stream function?
I'm hoping you can answer that one, or Sarah. I need help.
So, yeah, but I'm just looking this up. I was looking into this. So Bethany, maybe you can be the one to set it straight. I was just about to. Anyway, so
yeah,
tree density is supposed to be native, and then shrub sapling density is supposed to be native as well, and then herbaceous cover. But Bethany, is that still correct?
yes, I believe so. So for the density and the herbaceous cover, I think we are looking at native plant species.